Hi, I'm Andy Hawkins, Head of Application Development at Additive Industries. Today I'm going to give you an overview of a case study that we've been working on together with GK and Aerospace and Ansys regarding the utilisation of process simulation and multi-laser powder bed fusion to produce a large complex aerospace component.
Hi everyone, thank you for the invitation to today's presentation. My name is Enrique Escobar and I work as a Senior Application Engineer at Ansys. In this presentation I work together with my colleague Vishal Sharma. So at Ansys we focus in engineer simulation, and Ansys in this case develops, markets and support engineer software that can be used to predict how products should be designed.
Hi, I'm Catherine Butler, a methods engineer at GKN Aerospace. GKN has a key focus to develop laser powder bed technology for manufacture of notional applications for next-generation engine platforms. This enables GKN to establish additive manufacturing capabilities across the value chain, aligned to future engine requirements.
So, as an overview, Additive Industries, we're always looking to develop collaborative projects and ways of working to enable customers to get the most from their Metal Fab 1 system. We were approached by GK and Aerospace to look at one of their challenging large parts and produce it on the Metal Fab 1. We saw this as a great opportunity to scope a wider development project and case study. To that end, Ansys joined the project to bring to the collaboration their AM process simulation tools and expertise. So based on those three partners, a three-way project was scoped to produce a large GK and Aerospace part with the work shared between the three partners. The main work share was with GK and Aerospace looking at component identification, engineering requirements, post-processing, testing and inspection of the parts. We at Additive Industries looked after the build preparation side of things, all of the support design and the part manufacturing. And then Ansys came in with their process calibration, simulation, validation and generation of the compensated part geometry, which would be used as the final production part.
A H sector was selected for this case study. It's part of the turbine exhaust case for a turbofan engine. This part demonstrates the benefits of additive manufacturing for an improved business case through part consolidation, reduced material usage, improved build speeds compared to a single laser machine. However, it represents a significant challenge from a geometrical viewpoint. It has overhangs, thin walls, thin to thick melt area transitions, and is large scale. It has a geometrical tolerance requirement of plus and minus 1 mm. These factors combine to make this a challenging part to print. A successful manufacture of the H sector would support GK and Aerospace in development of design for additive manufacturing methods and tools, validation of simulation and distortion compensation methods, as well as confirming business case applicability.
In terms of the process simulation side of things, process simulation is something that Additive Industries are actively involved in on projects using various tools with the main objective to help our customers get the best from their Metal Fab 1 system. We see this as a key enabling technology to improve the quality of production components coming off the system. Some of the process tools commonly available on the market are evolving very quickly, becoming more accurate and more powerful as time develops. And it really gives some key benefits in predicting distortions in the part ahead of production, identifying critical areas of failure in a build setup, driving improvements in build setup, orientation and support design to increase the chance of a right first time solution. They also now enable you to output compensated pre-distorted models, taking into account all of the stresses in the build of a laser powder bed AM component. And the following case study, which we've worked together on, takes an example part through the full process simulation workflow to show how dimensional accuracy can be improved using these simulation tools. So the basic workflow we covered for this case study, which we'll detail in the following presentation, is following a series of basic steps. So the first step is to identify the component and define the requirements of acceptance for that component. The next stage is to calibrate the system and parameter set for a given material by producing a set of calibration test pieces. These test pieces are then cut and measured to give the input for Ansys to develop their process simulation models. We then orientate the build, lay it out, design the support structure. The next step then would be to simulate the build setup using the initial build setup, using this initial support design. Ansys will use their simulation tool to simulate the part. We then, in the scope of this project, have built the initial component to validate that simulation. So using the existing setup in a conventional manner, we then do a back-to-back comparison of 3D scanning that component and aligning it with the simulation to check that what the software is predicting is correct, both in magnitude and in areas of distortion. The next stage then, if we're happy with everything, is to generate a compensated model. Set up that build. So the compensated model is generated within the process simulation software. We then take that model as an output, as an STL format, set up the build, slice it, assign the lasers, build the final part, and then go through the final inspection process. And that's the basic workflow that we'll follow for this project.
So the first step is the calibration procedure, and this first step is needed in order to calibrate the simulation. So Ansys account for different type of analysis and different scale levels. And in this case study, we focus on what it is the inherent strain approach. The inherent strain approach is a very effective and efficient computational method that can be used to solve complex structures like the X sector. These residual strains are specific to the machine, the material, and also to the process parameters that have been used to print the part, and they represent the accumulation of different strain components. For the first steps, three calibration samples were printed and cut, and the process is not really, the calibration process is not limited only to this type of cantilever kind of samples, but in this case we use a cantilever since they're quite small and very easy to measure after cutoff. In the calibration procedure, we use optimization capabilities that are available in Ansys Mechanical.
The next stage in the process is to do the basic build setup and support design for the part using a conventional manner. So with this particular component, this particular H sector, we can actually fit 3 components on a single base plate in the Metal Fab 1. However, this study we're going to focus on just producing one component and dialing that in using the Ansys software tool and subsequent analysis methods. So the support design uses a relatively conventional approach for metal AM components. We're using a combination of some solid CAD-based supports, some solid connections to the base plate to resist stress and thermal distortion, and also some kind of break-off support structures, which in this case we generated using the Magix tool. These support structures allow certain features to be hand-dressed and subsequently cleaned up for the finished component. These also take into account things like powder removal, powder extraction, and also low risk to the build process. Once we've set up the build, we assign the process parameters, slice the build, and then because we're building a single large component, we're able to utilize our Additive Industries dynamic laser assignment tool. This tool allows us to assign up to 4 lasers to a single geometry very effectively, taking into account all of the quality and productivity factors that you need to, such as the gas flow, the spatter formation, all of these things. So this is processed in the conventional manner, and then we can move to step 3 of producing the test part. The first part we produced based on this support design allows comparison with the results of the simulation carried out by Ansys. What we found with the first build, as you can see on the pictures, is no visible cracks or failure of support structures. However, what we do see is some buckling of the tall hollow support pillars, and we also see some shift lines at the base and top of the hollow channel within the vane geometry of the component. Also, a very large shift line appears on the top of where we have a large change in cross-sectional area at the top flange of the component. These are all areas that we need to focus on with the subsequent compensation.
Now, based on the supports and the orientation that was selected in step number 2 and number 3, an initial part was printed. So the initial part didn't have any kind of input from the simulation tools, but the idea was to be able to compare the simulation results with the scan geometry of this first try. So in this part, there were not really clear cracks or failure of the support structure, but there was some evidence of large deformation, kind of sort of buckling, and also sort of a shift line at the top of the casing. Now, in the fourth step, where we performed the first simulation of the sector, we used Ansys Workbench Additive. So Ansys Workbench Additive, it provides a very flexible environment to simulate the IT manufacturing build process with a very efficient HPC performance, which is a must for large geometries like the X sector. The part, the supports, and the base plates, they were included on the setup of the simulation, and the input values that were obtained from the step number 1, the calibration procedure, were used in this case as an input for the simulation. In the simulation results, we identify large deflection and large distortion in some areas, with a maximum deformation in the flange region.
Once the part has been manufactured, the base plate distortion was measured using a feeler gauge to confirm the flatness. The distortion was found to be negligible and localized to one corner of the plate. The part was 3D scanned using a Romer arm laser scanner, and the surface profile compared to the nominal CAD geometry using a best fit function. The part was then stress relieved in a vacuum furnace. It was rescanned after stress relief to compare the distortion pre and post heat treatment. The results presented here are post heat treatment. The data shows there are a number of areas where the part was outside of the required surface profile tolerance. Most noticeably, around 3 mm on the flange and 2.5 mm on the vane. The results were shared with Ansys so that their software could be used to create a compensated geometry, which when printed should result in a part which meets the surface profile tolerance requirements.
In step number 6, a compensated geometry was generated based on the results that were obtained from the simulation. The distortion compensation, what it does is that it applies the magnitude of the distortion at every location and reverses it on the surface of the geometry. In this case, the sector was printed using the compensated geometry, but there was not enough to compensate also the shift line that was located at the top casing. And this is where new supports needed to be generated.
The compensated part was 3D scanned, and the resulting surface profile was compared to the nominal CAD geometry. Results indicated that the distortion in the flange and the vane were reduced significantly, but remained outside of the required tolerance. A large step was also observed where the support structure attaches to the upper overhang.
So, based on that, we decided to tackle some of these key problem areas where the magnitude of distortion was really quite high with an updated support design. So what we decided to do was remodel some solid CAD supports to the large flange areas where we were seeing a large change in cross-section, and also add some hollow constraining arms with a break-off interface attachment connecting down to the base plate to just give a little bit more kind of stiffness and rigidity to those vertical flange features. So, step 8, second iteration, simulation and compensation. The new support design simulated, the geometry is compensated in the same method as previously, and then comparing the compensated geometry to the CAD shows some areas still slightly outside of the tolerance. However, this is something that we feel is probably within the tolerance of the software. So by producing the part with this compensated model, we feel that we should still be within the tolerance required for the final component.
Finally, in step number 9, using the results from the second iteration, we were able to print a geometry that was between the required tolerance of 1 mm. Where the light distortion of the center vane was reduced about 2 orders of magnitude, and they were able to see in general like a much lower distortion on the overall H sector.
The second iteration of the compensated part was 3D scanned, and the surface profile was again compared to the nominal CAD geometry. This time, the data showed that the distortion on the flange had been reduced to 0.7 mm and the vane to 0.9 mm. The part was successfully printed within the required surface profile tolerance.
And just to tie things up, the support generation is the support removal and post-processing of the part is carried out, and we can see on the finished part here that we have a very nice, consistent-looking component that meets the engineering requirements set out by GK and Aerospace in this project. So just to conclude, this collaborative project has clearly demonstrated the capability of multi-laser powder bed fusion in combination with process simulation. We've demonstrated a workflow required to achieve improved geometric accuracy for large aerospace components. Also, by utilising the 4-laser full scan field capability of the Additive Industries Metal Fab 1 system in combination with Ansys process simulation software, it's been possible to produce a large part within a stated aerospace tolerance. The approach of process simulation followed by geometry compensation further unlocks the potential to manufacture large aerospace components in serial production. And finally, the collaboration between the 3 partners has been a really great way of pooling our shared resources and knowledge and understanding to produce a really great case study that demonstrates the real potential of metal AM.
I think different lessons were obtained from this workflow. Not only that we learn what are the design principles, or what type of design principle that will help in the production of complex components like DS sector, but we are also to see how we can use the power of simulation to unlock the production of large aerospace components. Finally, this study shows the great work that can be done by combining shared knowledge that Additive Industry, GK Aerospace, and Ansys have in different areas. Thank you one more time for joining the presentation today. I hope you enjoy this time. Thank you.